Hi guys and girls, this is Miss Pashower. We are working on, one of our last few lessons here of Unit 9, and it's not necessarily new information, it's just kind of some fun stuff about how you'd solve systems of quadratic functions. And remember, we're going to start by talking about what is a system. Okay, what does it mean to have a system of equations? So why don't we go ahead and start there? Here I've said, why don't we remember Unit 6, which was all about the entire idea of systems of linear equations, sorry. So a system of linear equations, if you remember, is simply a situation involving more than one equation. Okay, we had three, count them, different ways in which we solved systems. Okay, we did graphing, we did substitution, and we did elimination. We talked about when they're best used, and this file that you see here in front of you, this kind of whole chart, was something that we did at the end of the unit, and we talked about the different ways to solve and when were they best used and how you did it, and an example problem of each. Okay, I have the answer key to that form here. So I just kind of want to look down at the bottom towards the examples. Okay, that's a quick way I think to review. How did we do graphing? Well, how did we solve a system by graphing? All we did was we looked at, okay, here's my first linear equation, and that looks like it has a y-intercept of 3, and it goes up 2, so that must be that one there. Okay, my other one, remember graphing is always easiest when we're solving, when we have y alone, right? When we've solved for y, because then we can see the slope and the y-intercept. This pink one has a y-intercept down here at -4, and then its slope is -3/2, so that one must be here. What is the solution to this? What is the answer? Well, the answer is simply where they, ladies and gentlemen, intersect, right? That concept, that idea, is not going to go away today. That's basically how we're going to do it when we have parabolas. We're looking for where maybe two parabolas intersect, or where a parabola and a line might intersect. Okay, so that's graphing. Now, obviously, we know that sometimes graphing takes a little bit more time and it's a little tedious, so what other methods can we use? We can still use, this second one here was substitution. We can still use substitution when we start talking about combining linears and quadratics like we're going to do today. So when we did substitution, what did we do? Well, it looked to me like that x was the easiest one to get alone. So here, if you look at my steps here, it looks like I subtracted this 2y over to that side. Okay, I subtracted the 2y, and I got x equals 13 minus 2y. In my other equation, I found where x was, and I put 13 minus 2y. And then I figure out that y is 8, and once I figure out that y is 8, I can put that 8 either here, where I have a y, or here, where I have a y. Either one of the equations is fine. I actually put it in neither one of those. I actually put it here, where I have that y right there, because that one also works. Okay, so I put 8 here for y, and I figure out that x is -3 and y is +8. If we were to graph them, we would find that they intersect at x of -3 and y of +8, up there somewhere. Okay, elimination was kind of a fun one, and I'm not going to go through this one too much because when we do this with quadratics, elimination doesn't actually work. Why? Well, because this one's going to have an x and a y, but if this were a quadratic function, you'd have x squared plus 2y equals 6. And then, ladies and gentlemen, those won't cancel out because they're not like terms. So unfortunately, as we get into the actual notes we're going to take today, okay, you might want to start writing this down. Basically, we're doing Unit 9 lesson 8, solving systems with quadratic functions, and it says when solving systems of linear functions, we could use these three. We could use graphing, substitution, and elimination. Here in green, when we do this with also quadratic functions, we can only use these two, and those two are graphing and substitution. I think I spelled substitution wrong, sorry guys. Substitution. Okay, so let's look at an example problem. If you want to take some time and write those down, feel free, but I'm going to move on to an example problem. And we're going to do the same problem, but two ways. If I'm going to graph y equals 3x plus 2, that's going to be linear, right? This is going to be the one that's going to make a straight line. Why? Because there's no x squared value, it's just regular old x. This one, the second one, I would expect to have a parabola. Okay, it's a quadratic function, so it should graph as a parabola. A linear function will graph as a straight line. All right, that makes sense. So we're going to graph both of these and look for where they intersect. Well, if you have a parabola that does some sort of this shape, how many different ways could you hit that? Well, it's possible. Hopefully you're saying to yourself, oh, I would expect probably more than one answer. I'd expect probably two answers. Well, here in Desmos, I've done the graphs real quick. The linear one, I'll just kind of review how that works. That one we'll put in pink. That's going to have a y-intercept of positive 2, y-intercept of positive 2, and a slope of 3. So I go up 3 and over 1. Up 3 and over 1. Okay, up 3 and over 1. And I would have this pink straight line right there. If I do the parabola, well, that's going to take a lot more work to graph, right? A few different ways we could graph. We could try and factor it, see if it factored, and that would kind of help us with the x-intercepts. I don't know if this one factors, guys. To graph this one, we would either put it in software like Desmos, or we would use negative b over 2a, find our axis of symmetry, all that kind of good stuff. So this parabola here represents the exponential function. Where do they intersect? I think I'm going to erase some of my work here just to kind of see a little bit better. Looks to me like they intersect at right on the y-intercept, or y-axis. So that must be 0, 2 as an intersection point. And, oh, this one's nice. That must be x of negative 2 and y of also negative 2. Okay, so that's how you do it if you're graphing. How would you do it? By substitution. Hopefully I would get the same answers, right? So let's highlight these so we would look for, how I could compare the two and hopefully get the same answers when I'm done. If I'm substituting and both of these are solved for y, couldn't I take this piece here that equals y and just put it there? Kind of as if you're putting the equations equal to each other. So why don't we work this out? Why don't we do it the non-graphing way, the substituting way, see if it goes faster, see if it goes quicker, and compare and hopefully get the same answers when we're all the way done. So I've substituted. Instead of writing y, I put what was equal to y in the first equation. And now, because I have a quadratic, I'm going to look for all the different ways I can solve. So I think with solving, we're going to have to put everything on the same side. I'm crossing my fingers. Hopefully it will factor. Remember, factoring makes life easy. 6x minus 3x, because I had to subtract this over to the other side, is going to be positive 3x. And then also when I move the 2 over, okay, that's going to give me, oh, this could be nice. That's going to give me 0. So therefore, I can definitely factor this. It doesn't look the same as when we do this kind of factoring. I'm going to look, because I only have a binomial. So 0 equals, if this becomes 0, let's just erase it. What can I take out of both of those guys? What can I factor out as if you're doing the opposite of the distributive property? Well, they both have a 3, so I can take out a 3. And they both have an x, so I can take out an x. What's remaining? Okay, basically each term, what you're going to do is divide it by 3x. Divide by 3x and see what's left. 3x squared divided by 3x, well, there's only one thing left, and that's just the x plus 1. So what are my solutions here, guys? What's going to make this piece equal to 0? 3x equals 0. Well, x would have to itself be 0, right? What's going to make, new color, what's going to make this piece equal to 0? Well, x plus 1 equals 0. So therefore, all right, those are my two x values. X equals 0 and x equals negative 1. But those aren't points yet. That's just the x value. Remember over here we have a point. Oh my, I must have done something wrong. Oh no. Because here I have x of 0 and I have x of negative 2. So it looks to me like this one is correct. Let's see where I went wrong. Oh, you know what? I was wrong here in the first place. This is negative 2. Sorry, guys. So therefore, I am halfway through, and this is actually negative 1. Yeah, because this was x of negative 2. This is and so therefore, the same mistake here. Thank you so much for being patient with me, folks. So it looks instead like negative 1 comma negative 1. So how am I going to get these y values? How do I get this piece? How do I get the corresponding y value that goes with each one of these x values. Both of these x values are really just half of my answer. So when x equals 0, what does y equal? When x equals -1, what does y equal? Well, basically, substitute it back into what you started with. You can substitute it into either one. So if we have the option of substituting it into this one or that one, I don't know about you guys, but I'm going to do the first one. Because those numbers are easier. There's no x squared. It's much smaller. I think it'll be much quicker. So y equals 3x plus 2. Okay, let's write that down here just so I got it. Y equals 3x plus 2. So when x is 0, I would say y equals 3 times 0 plus 2. All of that's going to basically cancel, so y equals 2. So therefore, my answer, guys and girls, is a point. Okay, a point needs both an x and a y because we were expecting these line and parabola to hit in two spots. I'm going to have an intersection there and an intersection there. So this here is my first point. That's basically half of my answer. And how do I find the other one? Well, I'm going to go back to over here when x is -1. Okay, when x is -1, what is y? When x is -1, what is y? And again, I think it's going to be easier to use that first equation of y equals 3x plus 2. Y equals 3 times -1 plus 2. Y equals -3 plus 2. So y then equals -1. So my final answer is going to be the point when x is -1 and y then also is -1. Okay, so let's highlight that. Maybe we'll put a big red box around it as well. But hopefully those match what I have over in my graphing. Do they match? Well, we have 0, 2, 0, 2. We have -1, -1, and -1, -1. Okay, so this is going to be what we were working on next time you come to class. Okay, that's kind of the whole overview of how we're going to do that. Okay, we can graph or we can use substitution. Okay, that's really all of the, specific skill type things. You might ask yourself, how many different types of solutions can we get? Is it possible to have a straight line and a parabola that never intersect? Oh yeah, definitely. Is it possible to have a parabola and a line intersect in just one position? Yeah, I think so. And is it possible, like we just had in the last one, obviously, to have it in two? Most definitely. Okay, so this is just kind of a summary. There's 3 different options. They could never hit, they could hit once, or they can hit in 2 spots. Okie dokie. And then I have a fun story problem that has to do with baseball. Okay, how far do you need to hit a baseball in order to really get a home run? Okay, if you've ever been inside a baseball stadium, we have kind of a wall here, right? So if these are, the cars out here in the parking lot, and this is home base where someone could possibly be a batter. Please forgive my drawing. And he's going to hit the ball. Well, you don't just want to hit it here to the end of the field. You have to hit it over the fence. It's got to get above whatever height that happens to be. So I'm using Desmos for these. A lot of our real-world applications in this scenario, we're probably going to use some graphing software. I'm not going to expect you to graph something like this, and we could obviously do that one's not so bad. But putting it into Desmos, putting it into your graphing calculator also helps to tell a good story. What's really happening? Okay, so this equation here, they're giving us the equation. This equation here, oopsie, so sorry, has to do with the path of the baseball. Okay, the path of the baseball after it is hit can be modeled by this equation. Okay, I also have the roof of the gym, and I also have this wall of the gym. So my situation is a little bit even more complex than this one. Okay, I have a wall that goes straight up and down, and I have a roof that kind of goes at this angle, and I need to get it. I need to hit my baseball all the way over this roof here. So what's really happening? Well, this one says basically the question that is posed is this one here in red. Does the baseball hit the roof or does it get a home run? And maybe for those of us who don't understand baseball, I should explain. If you hit the ball out of the park, out of the entire field, stadium, then you get a home run. All right, so this person is playing baseball, I think more in like a gym, in gym class, and they want to know if they have this mathematical information here and here and here, will their baseball be a home run? Okay, so here in red, I put this in Desmos, and it looks like the path of a baseball, right? That makes sense. Here in blue, and maybe I'll use the right colors, is the roof. Okay, so this one is the roof. Here in blue is the roof. I have kind of like this diagonal type roof of my gym. And then I also have the back wall of the gym. Okay, so here's the back wall of the gym. Some of these lines don't necessarily make sense as far as what's going on. I think that the roof doesn't actually include this piece here. Okay, you're looking for just kind of where these lines intersect each other. So why don't I kind of highlight or make these a little bit darker? This is going to be the wall, right? The wall doesn't go past the roof. It's just that piece going up to it. And then this is going to be the roof. Okay, can you kind of visualize how that would work? You have a wall in the gym here. You have a roof that goes at kind of an angle going outside, right? There's the roof. So does my baseball actually make a home run? All you have to do is look at the situation and understand what's going on. Does the red line get out over here past the roof? Doesn't look like it, right? Doesn't look so much like it. So a lot of these real world applications I think are kind of fun to graph, and you can really see what's going on with a picture. Again, use some graphing software to help you out. What is this baseball really going to do? It's going to leave the batter's bat, go up, over, and hit here, and then probably bounce down. It looks like it'd be a good hit. Maybe it'd get a double or a triple, but not a home run in the sense that it's going to go out of the park. Okay, so that's all, ladies and gentlemen. Feel free to go back and review anything you might want to go back and review, but I will see you in class tomorrow. Let me know if you have any questions then. Have a great night.